Hello friends of .NET, I'm Emil Landworth and you can find me on Twitter @terrajobs. So in this episode we are hopefully going to wrap up our IL emitter. So last week what we did is we moved away from our hard-coded hello world and we emitted enough of the IL construct so that we can actually compile hello world from sources. We also included some stuff that was not strictly speaking for hello world, strictly speaking required for hello world. One of them was string concatenation, so we can actually do something meaningful where we can ask the user for the name and then concatenate a message and then print that. But we certainly don't handle all the expressions yet, certainly not all the binary expressions at least. So today what we will do is we will handle more of the binary expressions. We will handle all the remaining expressions, conversions, unary expressions. I should probably turn off my Telegram here, so otherwise it will annoy. Otherwise it will annoy me more and more with notifications popping up. We will do statements, so specifically loops and if statements, because they will require labels, and that's some interesting stuff we can do there. And I think that's pretty much all I had for today. Let me quickly check my notes, but yeah, that's pretty much it. So it will be fun today. I think we will have a lot of fun. Wow, Imo got himself a new microphone. Yes, I was tired of the mic quality in this room. Like, one of the challenges here is I'm sitting in the living room, which has a very high ceiling and hardwood floor and still no furniture. So it's acoustic-wise not the best environment to actually record. So I had the option to either buy myself a better mic or change the house. I went for the better mic. Yeah, video and sound are not completely in sync. That's probably true because I think the timing is now off because I disabled some of the filters. So I probably have to fix that at some point. But you know, most of the time you will see me as a little icon at the bottom right corner. So probably will not make a huge difference. Is the background music intentional? It is. It's an experiment to see whether that will work for us or not. But hopefully it's not too distracting. I chose something relatively quiet and also appropriate for streaming, so I don't get into issues with the content police. So that should be fine. All right, so then let's move to the coding portion. So as usually, we will start with our pull request to make sure that we don't have a lot of stuff going on. We do have a lot of stuff going on. Wow, that's quite a bit. So before we go in there, I want to probably talk a little bit about the issues here. So a few days ago I sat down and went over all the things I still want to do, at least the things that came to my mind. This is by nowhere near a complete list either, but it's basically all the stuff that at some point I did and then forgot about it, so I added it here so we don't forget about it. I tagged all the ones that I expect to do on the stream. So for example, optimizing string concatenation was brought up last time. And so all the ones that are tagged with episode, you can expect me to at some point handle on air. I tagged the ones that are either a lot of work or are, basically just complicated enough that I think it's worthwhile to talk about, or just stuff that makes sense to do on the stream. And then there are some issues here where I think it's minor, like print should accept any. So basically our print statement only accepts strings right now, which is slightly annoying when you want to just print, a number to the console. You have to convert the int first to a string and then call print on it. And so we should just replace this to take any, which is not a lot of work. It's a few lines of code when you know where it is. So this is one of those things that if you really urge to submit a PR, those are good ones to submit to because they're easy to do and I'm very likely to merge them. All right, so then let's look at the actual PRs here. Let's start maybe with the bottom up and then see where we are. Oh, that's an interesting one. Yeah, so editor config. Yeah, editor config is one of those things we can edit. It will not do much for us, unfortunately, because I think at this point VS Code still doesn't support editor config in all cases. So that's why I think somebody already added one. and it still doesn't name the fields the way I want. Actually clicked on the wrong tab. I think that's the one I wanted to look at. Okay, so let's quickly take a look. So that's in the root. That's fine. Space changes. Yeah, there's a lot of stuff going on here. I think this is the one I probably have to take a look offline because I don't even know what's going on here. Let's talk about this one here first. So this is a simple one. Yeah, that one I'm not sure I like, to be honest. So I guess this function just moved for some reason. Why did the function move? Single commit. I mean, it's not strictly speaking required to do these nitpicking things, but I try to keep my commits clean so that it's clear what's happening. And like things like this, when you move a function from the lower part to the upper part, it's just asking for trouble. So it seems worthwhile to just split this out into something else. Oh my god, GitHub. What is happening here? Why do you keep doing this? I guess in this case it doesn't matter too much, but I really wish when I submit a comment it does not do this start review thing, because it's super annoying to fix, or at least give me a button to promote this thing to an individual comment. Let's do this. Always seems hard to say request changes, but hey. A typo. Oh yes. If I would get a penny every single time I get caught having a typo, I'd be rich at this point. Yeah, that's an interesting one. So I think, okay, this is based on his own PR from earlier. So, but it looks interesting. It's basically, the way I understand it is, yeah, that's exactly what I thought we should be doing. So today what we do is when we emit code, when we actually build our code, we have this directory.build.props and directory.build.targets, which effectively takes care of calling our compiler. And we can extract it into an MS Build SDK, which now means we can actually put the project files that are on disk. Instead of saying Microsoft.NET SDK, it would say Minsk.SDK in the project file. And the project file, the SDK then can be NuGet package. And the NuGet package would effectively contain a binary of our compiler. And then the MS Build targets that we currently have in the directory .build.props and .targets, which now means if somebody uploads the project file somewhere and we just clone it locally from a repository, we can actually build it. Right? We don't have to have the compiler somewhere available in source form, which is actually quite nice. So that's actually something that I think will be very cool. I clicked the wrong button again. All right. All right, so that should be it for PRs today. So now let's actually create a new branch for our episode, which I believe is episode 20 at this point. Right, if people in the chat find the music too distracting, let me know and I can turn it off. I actually like it to actually hear something in my head, so it's not complete silence when I don't talk. Makes it slightly less awkward, I guess. All right, so one thing I want to fix is our compilation is relatively slow. So we can actually show this. Samples. If I say .NET build. I mean, considering that what we compile is not a lot of code, it is slow. It is slow for a couple of reasons. One of the reasons is because we are still building the compiler itself every single time. So that's not helping our compile speed. But we also spend a decent amount of time in the compiler itself. And the reason we're doing this is because we are passing in the entirety of the assemblies from that core app 3.1. And then the only thing we pick out are effectively our built-in types, console, and that sort of thing. So we can be a bit smarter than that. So what I want to do here, in this thing here, instead of passing all references, which I do here, I will filter down to the ones that I know we actually need. And there's two ways I can do this. I could either disable implicit references entirely, which is a bit of a heavy hammer, or I can just remove the ones that I know are not relevant. So I'm going with the latter right now because it's seems like an easier fix. Although easier is relative. So what we'll say is we will say reference path remove. And we can say file name is not system runtime. So basically this will remove everything but the assembly where the file name is system runtime. This will not work because we need more than system runtime, but I want to see it fail. Yes. So the required type console cannot be resolved among the given references, because right now we only resolve against system runtime. So now the question is, where's console? Which we can quickly answer from this beautiful website here, which I wrote. So I might be slightly biased. So what we can see here is that console ships in system.console. That's the assembly name. So we can just copy and paste this guy. And then we can say, remove everything where it's neither system runtime nor console. So if you didn't know, you can actually have attribute value spanning multiple lines, which makes this much easier to read. So this is actually valid XML, believe it or not. Hey, press the wrong button. I don't know why this keeps happening. I wrote APIs of .NET. That is correct. Yes. So now it should be building for us. Maybe I fucked up. Oh, yeah. Boolean logic is hard, as it turns out. All right, so now it builds, and it is still not amazingly fast, but it is certainly faster than it used to be. So I call this already a success. remove necessary references from compilation. Yes, I am spell checking. Good. All right. So then let's create our PR branch. PR create. Isn't there also a flag for draft? I think there is, right? This is fill. Perfect. Man, I really love the GitHub CLI. It's so much nicer to not have to go to the website to just do basic stuff like this. I think you can even check. Isn't there like a PR status thing? There is, yeah, here we go. So you can even check where your CI status is without actually opening the website. I mean, the amount of times I have just navigated to a browser, typed the URL just to know whether my CI passed or not. And now I no longer have to do that, which is quite nice. All right, so now let's actually go to our emitter here. Emitter. Also just realized one thing. I probably should have pulled in the changes that we got from merging. All right, so then much more of a cleaner start. Oh yes, show my screen. Wouldn't that be nice? It's not a professional screen if you're not on the wrong scene at least once. That is very true. All right. So much for you only see me in the small corner. Sometimes you see me also in the big corner. All right, so what I just did, I think probably the last thing you saw was me typing some stuff. But basically what I did is I did this thing here where we just excluded everything that is not system runtime or system console. And then I just rebased some branches. The other thing I was quickly showing was you can ask the GitHub CLI to tell you what your status is with CI. So I know that I just pushed to the branch and CI is passing, which is super nice. So cool stuff. All right, so now let's actually go to the emitter and actually do something useful here. How about we collapse the things we have done? So that one slightly easier. So we have, so the emit statement is just dispatching. Emit variable declaration is done. So we have to do label statement, go to statement, conditional go to statement. Return is done. Expression statement is done. This is just a dispatcher, which is also done. Little expression is done. Variable expression is done. Assignment done. Unary not done. Binary not completed. Call expression done, I believe. And then conversion expression. So basically these are the ones we have to still do today. One thing I want to fix as well, which I talked about last time, was this one here. So in C# and same in our language, if you have a method that returns void, you basically never have to write a return statement, right? You can just write your method and then after the last line of your method executes, there's an implicit return to the caller, right? If you have a function that actually returns a value, there's no implicit because you have to say what the value is, right? And so that means that effectively when we have a void function, also known as a procedure, then there might be no return statement. However, that is not legal in IL, and it kind of makes sense because return is the thing that actually causes the the runtime to actually return to the caller, right? So we need to have always a return statement in the method body. And so the way I fix this is by saying, well, if the function type is void, then I just emit an opcode here, which kind of works, right? But it seems, generally speaking, not great if the emitter is not actually emitting what our intermediate representation says. And this can bite you later when you actually try to do modifications, optimizations in your intermediate representation, because it's not a truthful representation of what you're actually emitting. So we should remove this fix here and instead make sure that when we lower our representation, that it actually has this return statement already in it, which is not super hard because we already have a lowerer here where we do a bunch of stuff. If I open the right file, of course. Like, for example, rewriting for statements to while statements and stuff like that. But there's also some things like the flattening here where effectively we remove all blocks and just have, a single bound block statement with all the instructions in there. And so what I will just do here is I will add that to this. And in order for us to do that, we need to know what the function signature is. So the easiest way to do this is to just say, pass me the function that you want to actually lower. And then we can just forward this. So let's actually go here. And then I think somewhere here, I would have to say if function type is type symbol void. Now we have to know, is there actually a need for a return statement, right? So if the very last statement is, for example, a goto statement, that means you have a loop, and inside the loop you either terminate or you don't terminate, but then there's a return statement somewhere in the loop. So what I want to do here is I want to do something like if builder statements, I guess builder count. So if we have any statements at all, actually if we don't have statements, then we need one for sure. So if we don't have statements, or the last statement can fall through last statement, then we need a return statement. So I can say add new bound return statement. And of course we don't have an expression here because that's a void function. So what does can fall through mean? So basically we know when things can't fall through. So if bound statement kind is either a bound node kind return statement, and goto statement, right? Because return statements, okay, we already handled it, but return statements also unconditionally go somewhere else. Goto statement unconditionally goes somewhere else. So we have a conditional goto statement which can fall through if the condition doesn't hold. So only in the cases where the last statement can actually fall through, we need to return. And so this is what this one is checking. So now let's go to the binder. Let's actually pass in the function. So here we are processing this function here. So that's trivial. It's this function. And then the global one, we would pass in the main function. And in the script function, we pass in the script function. Hello to Germany. Yes, you should watch the series from the beginning. It's fun. And it's at this point, after this episode, 40 hours of content. Jesus Christ. That's a lot of stuff. All right, let's have a function here. Do it. And let's say this function is empty. Or let's say dump do it. And here's our implicit return. Now let's say return. In which case we didn't add one, so it just remained the way it is. Now let's check what happens here. While true. Huh. Yeah, this is something where our optimizer is probably not smart enough, because clearly this is causing a problem now, because we effectively treat a conditional goto as fall through. However, we can't just say if it's a conditional goto statement and the literal is true, because then the IL that we would emit would still be invalid, because if you actually have a branch instruction like this CLR will still reject the program on load, because you need to have a return statement, because it can fall through, I believe. I don't think it will make a check whether this expression here is always true. So in order for us to actually get rid of this, we would actually have to rewrite this one to an unconditional goto, which for now we don't want. So it's fine, I guess. Alright, so we just let this. This looks reasonable, we just pass it. Probably should add a note for ourselves to do. We don't rewrite conditional gotos where the condition is always true. We shouldn't handle this here, because then because we should really rewrite those to unconditional gotos in the first place. Unconditional, not a word? No, it is a word if you spell it correctly. All right, let's do this here. Let's call this expand implicit returns. Sweet. Actually, not quite. Should have removed this one here. That was the whole point. All right, let's just alter the last commit. All right. Sweet, now we can say function body is also done. All right, unary expressions. Let's do unary expressions. Or maybe, well, actually, let's do conversions first. So conversions, we already give you a sense of what they do. Let's go to the evaluator, where we just evaluate them. So logically speaking, what we do here is we say if you're just converting to any, we don't have to do anything, because we already have a boxed representation because evaluate expression returns an object. And converting to any is effectively just casting to object, which in IL speak means you are boxing, potentially, right? If it's a reference type, in our case, you only have one, which is string. You have to do nothing. But if you convert int to string, if you convert int to object, then you have to box the int. So in IL, you have to emit an instruction for that. So we would have to basically emit an instruction here that would box. If we convert to bool, or if you convert to int or to string, what I will do is I will just literally emit a call to the convert method. Because the nice thing with the convert method is it handles already all the complicated cases. And so we don't have to deal with that. So basically what we need to do is you have to import our to bool, to int, to string methods, and then we just call them as methods. So in our case, that would mean, if we go up here in our importer, we just add a few entries here. So that would be system convert. Let's start with to boolean. And this one would take an object. And we call this, what is it? Convert to boolean reference. And then we have to int 32 and to string. And they all take object. So that would be easy. To int 32 to, what is that? To string. All right, now let's create a bunch of fields. So yeah, the first thing we need to do is emit the box, because basically the flow is now, I always have to box, I always have to convert whatever the argument is to object. If the target type is any, I have to do nothing. If the target type is any other type, I just call the corresponding function, because they all take object. So boxing is always necessary. So in that sense, let's start with this. We would say emit expression node expression. And then we have to box, potentially, right? So if node type, I guess you can say var needs boxing. Node type is type symbol bool or int. Really the question we should be asking here is the reference type. Which we could consider exposing on the type symbol itself. But I don't feel like it right now, so good enough. If needs boxing. Then we have to say IL processor emit opcodes box. What's funny with box is it has an argument, and the argument is the value type you're boxing from. I don't quite know why they need that, but that is what you have to do. So we have to now say what is our type, and that is known types for node expression type. Actually, that's a good point. That would be node expression type, not node type. Then we can say if node type is type symbol any, then I can say we're already done because you already converted it to any. Else if node type equals type symbol boolean, int32, and then lastly string. IL processor call, emit opcodes call for convert to boolean. And then convert to string here, right? And then else, that would mean we have no idea what this is, so throw new exception. Unexpected conversion from node expression type to node type. Let's see what happens here. So we now go to our sample app here and just try to do some conversions. Let x equals true. I guess we can say string for true. Int for 42. And any for string. And then we say any for false. Just to see what happens here. So did I understand correctly that the runtime doesn't allow for an infinite empty while loop? No, what I meant is the runtime when you load a method, it basically says, okay, I need to now generate IL for that method body, and so it runs a thing called p-verify, which basically ensures that your IL is valid, which is basically things like, is your stack balanced on all the times. And so one of the requirements is that your method has to return. So if you have a void return, but you don't actually have a return statement or return opcode anywhere in the method, that's a bug. So if your last statement is a branch that is conditional on something, and it's not followed by a return statement, the runtime, I don't think, checks whether the condition happens to be literal that is always true. I think the runtime just says like your program is malformed. And that's why I said like we always have to add the return statement, even if the statement before it is go to conditioned on the literal true, right? Because operationally, yes, the statement is always true. However, like probably shouldn't emit a conditional go to anyway, or optimizer should rewrite this to a go to statement. And if you have a regular go to statement, same in IL, then the runtime will say, yep, that statement can never fall through, so that's fine. I hope this makes more sense. Okay, system convert is also something we have to now add, which I believe is in runtime extensions, but let's verify this. System.convert. Yes, it is in runtime extensions. Which now means I have to add this here and all right, let's see what we actually emitted. So we load a constant, we box a boolean, we call toString, we store it, we load the string 42, we call convert to int32, we store it, we load the string text, store it. Really? What happened there? Huh. I guess we handled that already. Because we basically do nothing. We just store it directly into a field. Then we load a constant, false. We box it as a boolean. And we store that. So that seems right. Let's run it and see whether it actually works. But it should. Yes, so there is no return statement here because that's an unconditional jump. So basically what the compiler does is what I'm not doing. So C# effectively emits this as a unconditional goto, which is basically what this branch thing here is. And so the runtime knows there is no fall through. So basically branch label is the equivalent of goto in our language. It is not the equivalent of goto with a condition. So that's the difference. That's why this is legal IL. If this one would be a conditional, like it would be like some sort of if statement before it, because I mean in IL there's also no such thing as a conditional goto, I guess, because that's a concept that only exists in intermediate representation. So in our case, we would have to have some sort of conditional check before, right? So that's why it's kind of apples to oranges comparison. So this one works just fine. I mean, obviously, right? I mean, you would think that C# gets infinite loops, right? Does that make sense? All right. Welcome to ML4G. I already looked at your PRs. You were busy. The SDK stuff looks super awesome. So I'm looking forward to see this flourishing even more. All right, so let me close this thing here. I think we are ready to commit this. Let's not commit this. And then I can say emit conversion. Emit conversion. Good enough. All right, so now let's talk about conversions done. Let's talk about unary expressions. So we don't have that many in the language to begin with. So we can say if node op is a bound unary operator. So you want to do kind here. So we have these. What else do we have? Logical negation. And then we'll like two more. Negation. Once complement. So identity is lame because we don't have to do anything. Logical negation is effectively not. Negation is negative, and this one is the once complement. So either way, we have to start with emit expression file processor node operand, and then we can say logical negation. I guess that doesn't help us much here. Emit opcodes. I think it's neg. Sorry, that's no, it's logical negation. No, this one is neg, and I think this one is Can never remember. What's the one's complement? Complement maybe? Is it not? It might be not. I think it's not. I think logic, because that's the thing I always fall over. I think logical negation is the comparison with 0. Let's check in SharpLab really quick what the thing is. So if we say var x equals okay, false. And then we say var y equals not x. Then yeah, that's not. Basically what happens here is we load x, we load false, and we compare. Yeah, so that's what I thought. So basically, and then let's say this one is, yeah, so one's complement is not denial. Okay, so then I got that right. So logical negation, basically, okay, we loaded the thing, and now what we need to emit here is IL processor emit opcodes load constant false effectively, and then we just say compare this. So basically what we're asking is, was this expression 0? In a very long-winded way. And then else we do the same thing. We can say throw new exception unexpected unary operator. No, I guess it's helpful to have an actual $sign here, and then it would be OP syntax kind, and then let's be nice here and say syntax kind not syntax kind, what is it? Syntax facts, I think. Syntax facts get text for this guy. Then we say here is node operand type. Let's check my exception because I don't trust myself. I have to say I like the music in the chat. I just don't like the fact that we have that many chat comments that just says what song is currently playing. But I could remove this if I would be willing to pay, as it always is. Alright, so the thing crashed, which is kind of what we expected. It's a bit weird though that we don't see the error message. Yeah, okay, so that's the output that I was hoping for, so it's somewhat readable if we mess up. I guess can run ms build. Why not? All right, it succeeded, so let's test the other expressions as well while we at it. Not true. Yeah, we don't do constant folding, so I can just what is that? Y Z. Sorry, not true. What was the other one we had? Plus 42. Minus 42. Jesus, I need to do better job with the shortcuts. I think there's some issue here where every time I toggle between screens, OBS ends up getting the focus, and then when I start typing, I effectively select a scene. So maybe one fix I can do is just hide the scenes, and maybe hide the sources so that I don't accidentally turn things on and off. And maybe that prevents it already. Sigh. Alright, so .NET build. Alright, so now let's look at the generated IL. Loading a constant, we perform not, which makes sense because that's the one's complement, yes. We load a constant true, we load the constant false, we compare them. That is not true. Makes sense. We load a constant 42. We save it. Yes. That's we don't do anything for plus, right? Because there's nothing to do. We just store the value as is. And then in minus, we load the constant. We perform a negate, and then we store it. All right, that seems reasonable. I dig it. All right, so we can undo this one. And then we can say emit unary expressions. That was easy. See, emitting IL is not that hard. It's mostly busy work. Alright, IL for unary done. Binary expressions. So binary expressions are unfortunately a lot more evolved. So I have to think about how I want to structure my conditions here, because otherwise it gets very quickly unreasonable and unreadable. So right now we're specially casing the string concat case, which is fine. Yeah, let's just go over the general case here. Say if what I want is a switch statement. I probably want this to be a switch statement, right? Okay, let's say switch node op kind go case bound node kind bound binary operator kind, I guess. Oh, that's the right thing. Yep, that is the right thing. All right. So in general, we need to just emit expression node op left. Again, passing in our IL processor. Do it for right. And then we just have to decide what to do for the operation. So for this one, it would be pretty straightforward. We would just say IL processor emit opcodes add. What is that? Subtract? Yep. Multiply. So one thing with IL is also there's different overloads. I guess that's a bad way to put it. There's not really so there's basically a multiplication operand, and then there's also one operator for multiply with overflow and then multiply with overflow unchecked. So that's the general thing here. Is also we have add, and then we have these other things. So when in C# when you say checked and unchecked, that kind of toggles what opcodes are being emitted. we don't care right now. We just keep our lives easy. Division. All right, logical and logical OR. So we are still cheating here. So what you want for logical and logical OR to do is you want this thing called short circuit evaluation, where when you say A and B, or A double and B really, you only want to evaluate B if A is true. If A is already false, you don't need to evaluate the second one to know that the whole expression is false, right? So that is important when you think of if statements where you say something like if X is not null and X dot something is not null and so on and so forth, because evaluating the second one would blow up because it's null, right? So we don't do this right now. So in our case, we would just literally just eagerly emit both sides and then just do an AND on the result, which is effectively the same thing as doing a bitwise AND. That is something we will add later. So in our case, they are literally the same right now. Bitwise AND, bitwise OR will both result in the same thing. And then we say to do implement short circuit evaluation. I don't think I can ever pronounce this, so I've given up. Yeah, I guess that works like this. XOR is, as you might have guessed, XOR. Okay, equals is a bit more involved. Let's handle less first. So less is less. Less than actually. Oh, actually, what? Am I? I'm blanking right now. Wasn't that less than? Did really forget how to emit this. I just did this the other day. Funny how that goes. Cool. Yeah, that is constant falling for you. C# already computed the value, so that's not helpful. Compare. That's why I couldn't find it. Yeah, so this is compare less than. And then this is compare greater than. Now there is no less or equals. The way you do less or equals is you basically check whether it is not greater. If that makes sense. So basically again we do the same pattern. We emit load constant false and we just compare. Right, C# does the same thing, I believe. So if you, I mean that's kind of what needs to happen here. So if we say I is this and then we say is this, then same thing happens here. It basically emits compare less than, load constant false, compare equal. We did the other case, but same thing really. So greater or equals is you compare less than, and then you check it's not that. And then again we say throw new exception, unexpected binary operator. All right, so that should be readable in case we didn't handle one. So now we have to think about equality a little bit. So equality is not that hard in the sense that there's an opcode that we can emit, compare equal. And I believe is there a not equal one? I don't think so. Probably it's the same pattern again. Let me quickly check whether that's true, but I believe that is true. Keep hitting save here for some reason. So it compares for equality and then compares for false again. So that's the same pattern that other things are doing. So we can do that too. However, that only works for value types, right? So for reference types, what you really want to do is you want to call object.equals, because that one will make sure the right things are happening. The way C# would do it, it would bind the operator against the operator methods. We don't do that. We just call object.equals, which for the most part will do the same thing anyway. But that's kind of language semantics of what you want equals to do. So basically, I think we want to do that, I believe. And then we will just effectively go here and special case if it's a reference type, which in our case would be if node OPK is bound binary equals let's do this. I mean, it's probably not the most readable, but it's probably good enough for now. So this way we can almost read the code. What? What did I do here? No. I just want to check the operators here. That would be not equals, right? Yeah, that seems about right. And then I think for readability, we probably want to do let's just so this is string concat. This would be string. Yeah, let's write it like that. Ay. Code organization is hard. All right, so now let's remove this guy here. Also, let's remove this guy here, and let's remove this guy here. think I probably want to do this the other way around. I probably want to say, let's first check this guy. Yeah, I guess readability is always going to be an interesting situation. We probably want to so we want to support equals for any, equals for string, right? And then the same thing happens here. Any. I think that probably makes the most sense. So it's either this. I think that's probably quite readable. And then basically what we would call here is our object equals, which I'm not sure we have imported yet. That would be call object equals reference. And then logically the same happens here. Except that we also need our comparison with false. Yeah, that seems pretty readable. All right, so now let's import our object equals, which let's put it here. Seems like the most important. Import object equals reference. That would be system object equals, and it takes 2 arguments. Oh, might as well take this one here. Right, that seems about right. Let's actually see whether we have any other special operators. So addition, subtraction, multiplication, division, bitwise and, bitwise or, bitwise XOR, equals, not equals, less, less or equals, greater, greater or equals, bitwise and, logical or, bitwise equals, addition. I think that's it. That's all the ones we have. I think. Let's do a few experimentations here. Let's check equals. 1 is 2. 1 is not 2. And let's have a string based one. Did you miss parents in those conditions? Inconceivable. No, because AND binds stronger than OR. I should probably make this more readable here in general. So this binds the way you would expect. We first check this and then that. So that's the right order of operations. All right, let's look at IL. All right, first one we just compare them. Second one we compare them with 0. Or if we compare the result of the comparison with 0, I should say. Then we load 2 strings. We call object equals with these guys. Yeah, that seems to work. We should be able to run it too. Doesn't do anything, but it's always good when the application doesn't crash when you run it. Not that this ever happened to me. Yeah. But yeah, let's actually check whether the result is something we would actually expect. Print y and then a and b. So what will we expect? We expect the output to be false and true. And false and true, right? Yep. All right, so unless I missed something, that seems to be it for binary expressions. Emit binary expressions. Why not put everything inside the switch? Well, I'm not sure you can. It's always weird when you have... I mean, I could take all of these stuff here and put it inside the switch statement. I mean, does this get easier to read? I don't know. I mean, this is one of those areas where I don't think there is a particular way to write it that is super nice, but I kind of like the special case thing at the beginning with comment headers. Okay, for aesthetic reasons, you probably want to have a blank line. And then effectively do the long tail. Seems easier to read. Is it possible to generate these switch case mapping variables in CodeGen? It would. I'm not sure that makes it easier though. Because keep in mind, you have to somehow have a data table somewhere that kind of tells you how to map these guys to each other, right? And I kind of doubt that that mapping table looks substantially shorter than this code here. So one thing I will do in a later episode, I don't know whether people are following the Rosin repo, but there's this new feature called source generators, which is, if you know what analyzers are a plugin to the compiler where you can write rules that effectively generate additional diagnostics. So your library authors can use that to, check that, people use the libraries correctly. So for example, XUnit has analyzers that tell you when you, let's say you put a effect attribute on a method, but the method takes arguments, right? That's of course legal C#, but that's not valid for the use of the library, because the library says if you want to have arguments to unit test, you have to use the theory attribute, not the fact attribute. That's the kind of thing that analyzers can do. Code generators are effectively similar. They are a plugin to the compiler. And what a code generator can do is the compiler gives it the compilation object, which has all the information about your source code. You can ask for symbols and all of that. And then you can use that to generate additional source code that gets compiled with the rest of the user's code. So for example, one thing we could do, which I actually have experimented with yesterday, or I think Monday or whatever. It's always a blur. We have these things here, for example, our syntax node, right? Syntax node. There's this function here called getChildren, right? And so right now what I do is I have effectively this method here which uses reflection to walk the type, which is not great performance-wise, right? So ideally what you want is you want getChildren to be a method on each of these particular syntax nodes, and basically it should dare effectively give you the children directly, right? But it's tedious to write because now I would have to make this thing virtual and override this for every single syntax node, which I think I had in the very beginning. I think in the earlier episodes you can see me defining the getChildren method for every single thing, and that's tedious, right? But what a code generator could do is we could just say, well, we just mark this thing as partial, and then a code generator can look at the constructor here, can figure out that the order in which syntax appears is first this one and then that one, and can then generate the getChildren method, right? And that's actually very clean because it now means all I have to now do is define my my method as partial, or my type as partial, and then Roslyn can generate or the code generator can generate the getChildren method. And that's quite neat. The other thing we could do is, because that's also tedious work, is our bound tree rewriter, right? This whole thing here, again, given the structure of our bound tree, we can generate all of this code because all of this code here can be effectively inferred from the shape of the type, right? So that's kind of thing where generators shine, because the rules of the code are effectively deducible by the shape of the program, right? So that's super nice. Versus this one here, that what we have here, this is not something that is kind of self-evident, right? Like somewhere there needs to be a mapping table that tells some party, a code generator or whatever, how these instructions map to, or how our logical instructions in the language map to physical IL instructions, right? And there's so many nuances and one-offs and whatever that I don't think this is, I mean, I guess in this case there are not that many, but like take this one here, right? How would you do this one in a data-driven way? It's so much easier to just write an if statement and just deal with that. So I think people overuse generators in general, or source generation in general, but I would only use it for cases where the mapping is trivial, because otherwise you just find a very convoluted way to write an if statement. It's always a blur. Somebody drank on coding. Actually, I have not done this in a very long time. But I remember vividly when I was younger, there was one incident where, I could party all day long. Sorry, I could party all weekend long, and I would still code up in, late in the night and all day long. And at some point I was heavily drinking and coding, and that's when I realized what feels good in the moment doesn't necessarily feel good in the morning. So sometimes when you look at the code, it doesn't look as smart as you thought it would. So version control is something that really helps you with that. All right, I think that's enough for expressions. Let's talk about statements. All right, so the nice thing is we have kind of reduced our entire statement to just these three, right? Everything we have, for loops, while loops, do while loops, if statement, all that stuff is basically just emitted to these three very primitive things. And they map relatively cleanly to IL. So let's start with the labeled statement. In our language, a labeled statement itself doesn't contain the statement. The next statement is the one that's being labeled. That is unfortunately not how IL works. In IL, when you emit a label, you literally have to put it on the statement itself. Or I don't even think that's an IL thing. That's more like the way our library Cecile does it. So what we have to do is we have to say IL processor emit actually I'm blanking now. What was it? No, actually there's no labels in Cecile, right? The way that works is, yeah, exactly. So the way that it works is Forget the label statement. Let's talk about the goto statement. So in our language, a goto statement basically has the label you want to jump to. The way this is being done in IL, you say IL emit opcodes branch. And then what you pass in is the instruction you want to branch to, because we give it an opcode here, but opcodes become instructions, and the instructions themselves are contained in the method body. So if you look at the IL processor body instructions, it's basically just an array of instruction objects, and instructions have an offset, but they also have a previous and a next pointer, which just points to the previous and next instruction, and Cecile wires this all up. So long story short, we somehow have to get the instruction from our node label. The way we can do this is we can cheat. We can say, well, we don't know the instruction yet, so how about we fake one up here? And the way you fake things up, you just create a knob, which in IL is basically nothing. A knob is something which doesn't get executed at all, and it's often used. I mean, even most processors have a knob instruction, which called no operation or whatever the long form is called, and it's useful to just have that, because sometimes you have to associate data with instructions, and so that's kind of how that works here as well. What we will do here is we will for now say, okay, we emitted this thing, but we don't have to remember that we have to patch up this instruction. So the way we do this is we have like a fix up kind of thing, where we say, okay, we need to fix up this instruction here, which we know which index this has. And we need to fix this up with the instruction that this label points to. If that makes sense. And so I will just have it basically a list of tuples probably to just deal with that. Actually, no, I don't want to do that at all. Instructions are mutable, which makes it easier for us to do. So I will just new up this guy. Actually, no, we want to... yeah, no, that works. That works. Oh, good. Let me first declare these guys here, so we actually know what we're talking about. So that would be private read-only list of tuples, and the tuple will be int instruction index, and it will take a bound label target, and we call this fix ups. And then every time we emit a method, a function, we clear this guy. That seems reasonable. And then this guy is very similar. The only difference here is you have to choose the opcode. So, and this is a node jump if true. Then we say opcodes branch true. Otherwise we say No, I can't sneeze. I hate when that happens. All right, so that's basically, we have to decide what the opcode is. So of course we need to emit first the emit expression L processor node condition, and that should happen first. Otherwise our thing will point to the wrong instruction. And then instead of doing this, we say this. And then a label statement just has to record what it actually labels, and that would be similar to this. We say let's call, no, not rename this, it would be a bad idea. Labels. So we basically say the next instruction will be this label. And probably, yeah, probably what we want to do here is slightly different. We don't want to use a tuple here. We probably want this to be a dictionary. Jesus. Indexed by our label. Alright, this is a dictionary of bound label. And then int, which is the instruction. And we call this labels. Good enough. And then same thing here. What do we do? Fix up. We need to clear our labels as well. So then after the method is emitted, we have to fix up our labels. Now we basically have to say for each var fix up in fixups. We have to say target is fix up. So this is the label. I have to think about this for a moment. So our fix up points to the label that we want. So this would be the label. And then the target instruction is labels. So let's call this target label. Target instruction. And then we basically only have to say IL processor body instructions for fix up instruction index. Instruction to fix up is this guy. And then we only have to say instruction to fix up operand is our target instruction. So this way we basically make our branch instructions point to the operand. So the operand is the other instruction we want to jump to. This is basically what this thing does. And then I think that's it. Should it be that easy? Well, let's see. Let's write a small program. For I 1 to 10 print string I. Yeah, that worked like a charm. Apparently the compiler crashed. Unable to cast object of type system in 32 to type instruction. What? Oh. Target instruction index. Target instruction. Hello. That was easy. So now let's actually look at the IL that we generated. All right, we load the value 1 stored in a local. We compare. No, we load then the number 10 stored in a local. Then we branch to O1D, which is here. Now we say load the first one, load the second one, compare them. If this is not less than, sorry, if this is not greater than, aka less than or equal to, then we go here, so the loop continues, otherwise you fall out of the loop. This is too hard to read. Let's decompile this to C#. Isn't that funny? You emit program in IL for a different language, but you can decompile it to C#. But that's effectively kind of what you would expect. So we basically say this is our loop counter I. The upper bound is 10. The reason I think this is not quite the canonical for loop here, normally you would expect this to be I equals 1 and then this just be literal. I think it's probably just the way our for loop is being emitted that it does not get detected by IL spy as a canonical for loop. But you know, the code is pretty readable and it basically does exactly what you think it does. So that's kind of neat. Yeah, I guess in my case, one of the things to consider here is I think we store, I guess we can't see it here. So this expression here we store in a local, which generally speaking is what you want, because we have to compare this value multiple times. And if this is a computed expression here, you don't want to recompute this expression every single time you compare the upper bound in the loop. However, I think that's the reason why this doesn't get detected as the normal for loop, because we always store it in local. Probably what we would have to do is special case it in the code generator and say if this is a literal, don't bother. Right? Don't store local, just always have a load constant instruction for that. But hey, not worth it. So that actually like that quite a bit. Is this all we had to do for today? I mean, these were our 3 instructions. And unless I have some glaring bug somewhere, this is it. This is all it took to emit IL. All right, let me quickly see this. Let's reset this guy. Okay, fine. Fine. The eternal perfectionist. Let's add the blank line to this one here. And then we can commit this, and we call this emit statements. Come on, commit emit remaining statements. Yeah, the built-in rand function is missing. That is a good point. So this one, yeah, I should probably add a to-do marker for that one. Call. Actually, throw new implement. Is this the only occurrence? Yeah. So the reason I don't have that yet is because that one is a bit more tricky. I mean, it's not that tricky, but if you look at the evaluator, so in this case, we have to have a random. So basically what we need is we have to have a field somewhere where we can store our random, so that every time we call it, we actually get a value back. I don't think there's any static methods on this guy, is there? No. So one way to do that is, how much time do we have? Yeah, we have. I think we have enough time to actually pull that off. How about this? We do this lazily. So we say private read only, not read only in our case. We say field definition. Random field definition. We have to import it. So there's a few things we need. We need the random type. So that would be random next reference. And we would need a type reference for random itself, so we can declare it. We probably also need the constructor for this guy, random CTOR reference. Yeah, so let's import this first. Random CTOR reference, or the other one, random next reference. Is that actually evaluate call expression? Yeah, we just have to instantiate this guy and then call next and passing in the value, so it's next of int. Okay, so this would be system random next, and the argument would be of type int32. The constructor would be ctor. Hopefully our resolve method can also resolve constructors, otherwise I have to do some work there. And then we also have to resolve the type. So that would be random reference, would be resolve type. Yeah. I guess, can this guy be null? I think it can be null, right? Didn't we do that? If Minsk name is null. Nice, okay, so we can pass in null for that. So we can say there is no Minsk name for that. But metadata name is system.random. Alright, so now we have these guys resolved. And now what we can do here is we can say, well, if random field definition is null, then we need one. Is new field definition. Let's call it $R&D. Field attributes, it would be static. It would be private. The type reference would be random reference. And then our type definition fields would get this field. Oh boy, we also need to now emit a constructor for our own type, which is somewhat unfortunate. Yeah, let's do that later. So we at least get going somewhere. Emit static constructor. To initialize field. But then after we have that, it's pretty straightforward. We basically just have to say emit. Okay, we already emitted the instruction. Yeah, we already emitted the load of the int. Now we only have to do call random next. However, that's an instance method, and it's also a virtual method, so it should be a call vert, which now means you also have to load the instance of the object, which in our case would be stored in the field. So we now have to say emit opcodes load static field, which is this guy here, load static field, and in our case that would be the random field definition. Okay, so now let's see what happens when we compile this program. Let's see what we have. An empty main. Nothing in there. Okay, that's what we expect. Now I can say var x equals R&D 15. Sweet, now we have our field. And then we basically say, okay, load the value 15. Actually, that's a good point. I'm unsure whether we first have to load the field and then the arguments, or whether we should do the other way around. If it's the other way around, we're kind of inconvenienced. Yeah, as you can tell here, this is clearly we did the other way around. So the decompiler is very confused. The decompiler thinks that our literal is the field reference. So it casts that to in random and then tries to invoke a method on that. Yeah, I'm pretty sure if we run this program, this will crash terribly bad. Yes, so and then it passes in the random field as the argument. So we did it the other way around. So one way to do it is to say special handling here. If node function is built-in functions R&D, let me do it this way. Right, so not bad. Now we have a static field. We invoke the next function over it. So this should generally work, except that it should crash with a null reference exception, because we don't initialize the field, but it should be, yeah, it's not an invalid program exception, so that's good. So at least our L is valid, but we have to do some work here. All right, so now we have to initialize this thing. So one thing is, right now we only have to do one thing, and that is this fun guy here. So we probably get away with just saying static constructor, new method definition, and then we say this is our class constructor, and then method attributes, static for sure. Is that a runtime special name? I think it needs to be private, and I think it needs to be marked special name. I could be wrong. And then the return type is known types, type symbol, void. Then we have to say type definition methods add static constructor. Yeah, let's move it at the beginning, just for shits and giggles. And then effectively the method body get IL processor. Yeah, you know what? Let's call this emit random field. Makes it slightly more readable. And then we say IL processor this guy, and then we can just say, well, what do we need to do? We need to emit opcode's new object, and then we have to pass in the constructor here, which is the random CTOR reference. And then we just have to store this result, store static field, random field definition. I believe that's right. Let's try this. I see RT special name. Yeah, I was thinking that yeah, runtime special name. Here we go. Try again. Let's look at C#. Yep. What did I say earlier about return statements? Unexpected end of block. Red. But other than that, it looks kind of what we would expect. It doesn't crash, so that's inspiring confidence. But maybe we should print it to the console, so we actually convince ourselves that something is happening here. Looks random to me. I mean, the zeros are kind of interesting that there are that many, but other than that, it looks random to me. Yeah, I mean, that clearly looks random. So how about we do what Lucas just suggested, leave special name in there as well. Yeah, there's no way this can be readable. But hey, maybe not have an indent that crazy. Looks somewhat reasonable. Should still work. Right, now our random function also does something meaningful. Let's reset this guy again. Emit code for built-in R&D function. This is cool. So I think that's pretty much all I have for today. Yeah, I think next week we're probably going to tackle some other stuff. So I think the next big issue for us is going to make debugging possible. However, before we do debugging, I think there's other things I would like to tackle. I'm not entirely sure yet what it is. Looking at my to-do list here on GitHub that I shared earlier, I think I will do a little bit more with CodeGen still. I think one of the things I want to do is I want to do constant folding. So constant folding is what the compiler does when you have constant expressions so that they get computed at compile time rather than at runtime. And once we have constant folding, we can also do dead code removal. So the thing I mentioned earlier with the while true statement, for example, where we have a conditional jump, but it's conditional on a literal. Those are the kind of things we would optimize, and then we should get very similar results for those simple cases. And then I think, I think after we did that, I think I will probably tackle another somewhat big item, which is whitespace and comments. So generally speaking, with whitespace, the way we have dealt with it right now is that we just discard it entirely, which is fine. However, when you think about a compiler, not just as a thing that, runs on the command line, but also as an IDE, you can't really completely discard whitespace, because the thing is, yes, your syntax tree has position information, so strictly speaking, you know where stuff comes from. But let's say, for example, you want to do some other interesting stuff. So for example, in C# you have, these IntelliSense documentation as comments, right? The summary tags and all of that. So if you want to do something like that, then, well, we can't completely discard it because we have to somehow access that data later. Probably when we define symbols to actually extract the comments and actually associate them with the symbol. So that's one thing I want to tackle as well. Another big thing, semi-big thing, is interpolated strings. So right now we have a print function, which is kind of neat, but C# has these interpolated strings, which I use all over the place, which is when you start a string with a $sign and you just say brace and then some expressions. I want to do something similar to that, which I think I also demoed in episode 1. I had already implemented. So those are the kind of things that I think we should be doing. And then debugging is, I think another big item for us, because debugging kind of has multiple sides to it, but it's not as hard as you might think it is, because we don't really have to provide a debugger. The only thing we have to do is we emit symbols so that we can just use the regular .NET debugger to debug our stuff. And for that to work, we have to emit sequence points. And sequence points require some changes to our intermediate representation in order to accommodate them. It's not going to be super complicated, but there's some fine tuning because you want some standard behavior. If you enter a method, usually the way C# works is that the open brace gets the sequence point in and of itself. So when you enter, you can basically set a breakpoint at the beginning of the method, and the same happens with the closing brace. So if you want to get a breakpoint every time the method is left, you don't have to set breakpoints in all the return statements. You can just set the breakpoint on the closing brace, right? So stuff like this we need to deal with. So it's similar to emitting IL. It's not hard. It's just, I guess, noisy or tedious, or lots of small things that make the overall experience quite nice. So those are, I think, the two big items for the compiler. And then there's related some issues that I want to tackle in the compiler, which has nothing to do with the compiler per se, but with the code base. So for example, I would like to use C#8's nullable reference types feature so that I can actually annotate in the compiler what things can be null. This is particularly useful in our syntax tree where constructs are optional, or in the bound tree where constructs are optional. And then hopefully that episode is somewhat interesting, not just for compiler authors or people who are interested in compilers, but how do you annotate a code base with nullable reference types, right? That would be a good episode to do. And then there's another one that I kind of hinted at today, which is I would like to have an episode on Roslyn code generators so that I can, instead of relying on reflection code at runtime where I walk the syntax trees and I think just the syntax trees, I would like to just emit some code into our compiler that effectively already does the walking of the tree. And so that's another interesting episode that I think would be good. That's, I think, probably another 10 episodes or so easily defined by just a few things here. And hopefully it doesn't get boring. So if you have other ideas, please file issues. Make sure to subscribe on YouTube. Make sure to follow on Twitch. And then hope to see you guys next week. Bye-bye.